Ate, Shio, hello, and a warm welcome to the first session of our new speaker series, A Sense of Place, the human connection to earth, water, and sky. Today, we are very honored to host Dr. Michael S. Kirk, a research scientist in the Heliophysics Science Division at NASA's Goddard Space Flight Center. The title of his talk is Echoes Between Earth and Sun, a conversation on the sun, space weather, and community connection. This series is hosted by the Indigenous Education Institute. Today's session is supported and funded by NASA HEAT, the Heliophysics Educational Activation Team, led by Dr. Michael Kirk. My name is Dr. Nancy Maryboy, and I'm from the Tsetlagai des White Rocks, Utah, and the San Juan Islands, Washington. I'm Diné and Tsalagi, that means Cherokee and Navajo. My Diné clan is Bibatoni, the Deer Springs clan, and Senjakini, the Cliff Dweller clan, which has ancient relationships with Santa Clara Pueblo. My Cherokee name is Tsawayuga, and I am from the Cherokee Bird Clan. I'm an affiliate professor in the Department of Environmental Studies and Forestry at the University of Washington. I'm also the founding president and executive director of the Indigenous Education Institute, which has been in existence for 30 years. We are located in the San Juan Islands of Washington State and on the Navajo Nation. IEI, the Indigenous Education Institute, is an Indigenous institution with a mission of preserving, protecting, and applying traditional Indigenous knowledge today. We also honor our many non-Indigenous allies from around the world and work with them in dynamic and collaborative relationships. I would like to begin today with a heartfelt acknowledgement of the Indigenous peoples of our Mother Earth, to honor our many participants from around the world. I also want to acknowledge that I currently reside on the ancestral lands of the saltwater salmon people of the Salish Sea, who have called this place home since time immemorial. I honor the inherent and acquired treaty rights of these Indigenous peoples. The speakers and presentations in this series have been chosen to reflect an awareness of the foundations of traditional Indigenous knowing and living. We also honor and work with practitioners of Western science, bringing the two ways together in a collaborative process of integrity and respect. We use the concept collaboration with integrity, the title of one of our books. In this series, we are focusing on the human connection with our earth, waters, and sky. A major focus for this speaker series is expanding awareness and understanding of cultural differences and cultural similarities, and to support successful and diverse collaborative working relationships, whether it be at NASA HEAT, Johns Hopkins University Applied Physics Lab, National Science Foundation, or in education, health, astronomy, national resource management, museums, science centers, national parks, and tribal communities. I want to personally thank you for attending this webinar. The interest you have shown is heartwarming. We have many people registered from all across the United States and Canada. We have participants from around the world, including Guam, Great Britain, and Spain, to name but a few. It is also interesting for me that we have many different tribes represented in our registrations for this presentation today. We also welcome many classrooms and professors who have registered for this event. Before we continue, I would like to ask you to put any questions for the presenters into the question and answer box and not into the chat box. This will enable us to better serve you towards the end of this presentation. We are honored to have Dr. Martin Storsteck from Oregon State University to serve as our question moderator. I would now like to introduce Dr. Michael Kirk, my friend and colleague, whose talk is entitled Echoes Between Earth and Sun, a conversation on the sun, space weather, and community connection. Michael?
Thanks, Nancy. It's a real pleasure to be here, and thank you to all of you for having me in the space to talk a little bit about the sun, the earth, and some of the work that we've been doing at HEAT with Indigenous Education Institute and other partners. So, extremely happy to be here and share some things today. But first, I'm going to share my PowerPoint slide because I'm much more comfortable speaking when I have a PowerPoint slide in front of me. So yeah, thanks for the introduction. I come to you from the Pacific Northwest. That's where I'm physically located, although I'm based out of NASA's Goddard Space Flight Center. So this is where I am approximately. If you know your geography well, you'll be able to point out Portland, Oregon on the map at the confluence of the Willamette and the Columbia rivers. But I think not only that, but where Nancy is located too is captured in this image. I particularly like this image, and I like starting off this way because it gives you a little bit of context, not only from where I was born and grew up in the Pacific Northwest, where I am now, but also where some of our partners are that we're working on this project, which is, you can see, I think if you zoom in or squint, you can see Friday Harbor from this image. This is an image from the International Space Station, taken on a glorious sunny day in the Pacific Northwest with the Cascade Mountains highlighted in white there. I also like this map because it showcases a little bit more of the relationship between not only where I live and where I grew up, but with the universe beyond. Because you can see, like, I could even zoom in. I could tell you where I was born. Like, I know where along the Willamette River that bends in just the right way, and I can pinpoint that, so I could get within walking distance even from this view. But it also shows you the curvature of the Earth and then the deep space beyond. So it shows you a little bit about where we are centered, but that in fact we're part of a bigger system. We're part of the solar system, and we're part of a larger entity. So to give you a little bit more of a formal definition of who I am and where I've come from, I'll start off with my roles at NASA. So I work out of NASA's Goddard Space Flight Center, but I'm remotely based in Portland, Oregon. I have four different significant roles at NASA's Goddard Space Flight Center. First and foremost, I have the pleasure of leading the NASA's Heliophysics Education Activation Team. This group is a group of people that exist across the country that have come together to engage communities on heliophysics education, understanding the Sun-Earth connection, and being able to explain it to learners of all ages. In addition, I am a deputy mission scientist on the Punch mission. This is a recent mission that launched just earlier this year. Is taking some gorgeous images of the space weather and of material coming off the sun. So there's been some great press releases on it, but I have a sneak peek. There's going to be more soon, so stay tuned for that. Keep your eyes out for more exciting science coming in from Punch. I'm also working on the Sunset mission. This is a CubeSat about the size of a shoebox that we're hoping to launch in 2026. This is going to showcase new technologies on how you can take deep images of the sun and the space beyond the sun. And I'm in charge of the software pipeline for that, so I do a lot of programming around that. And then last but certainly not least is the Center for Helioanalytics, where we're looking to bridge science and data science in heliophysics. How do we actually take analytical processes, modern methods, and bring them into science to do discovery science? But my path to getting here was not straight. So this is sort of a schematic diagram of the path I took. And so I grew up in McMinnville, Oregon. It's a small town a little bit south of Portland. When I was growing up, there was about 25,000 people. It has grown significantly since then. I went to undergraduate at Whitman College in Walla Walla, Washington, where I was majoring in physics and astronomy there. And then sort of floundered for a bit and ended up at NASA's Goddard Space Flight Center working as a contractor, a systems engineer on the Solar Dynamics Observatory mission before it launched. They liked the work I was doing and so told me I should go to graduate school. I went to New Mexico State University in Las Cruces, New Mexico for my master's and PhD, and then came back to Goddard again on the NASA postdoctoral program. Then after the postdoctoral program, moved over to Catholic University, still doing solar physics research in the DC area. Moved on to a private space company called Orion Space Solutions, based out of Colorado, and then came back to NASA in the position I have now about 3 years ago. This path is, when it's charted out like this for you, it seems relatively straightforward, as if this was all planned. In fact, I can very definitively say that this was not all planned. In fact, very little of it was actually planned, and most of it happened as life does, as you're interested in things and opportunities arrive or barriers come up in your way, that you change course. So the arrows are significant in this, and none of them are straight. All of them have bends in them. All of them take different paths. And that's sort of emblematic of really how my path evolved in that I could go on for a full hour about, coming out of undergraduate and not really sure what to do with my physics degree and ended up working as a caterer and as a landscaper, or canning cherries in Yamhill, Oregon for a summer. But that's usually not what people want to hear about. They want to hear about the success, the milestones. So these are the milestones. But I think talking with students, especially, it's important to highlight the aspects that even coming to a place like NASA, even becoming a scientist, the paths aren't straight and things move significantly. Um, so what actually derives and pulls all these things together? Well, I think thinking about this for a little bit, there are two things that really unite that path into one coherent idea. One is a fascination with the sun and data science. I've loved computers and technology, but also astronomy and how the world around us, the universe around us behaves. But then also a commitment to helping all of us understand it better. The idea that being able to ask a question and figure out the answer is something that's fundamental to the way that I work in this in my career, but also in life. Like I want people to be curious and to ask questions and to be able to investigate it on their own right, so that they have the right tools and the right tools to be able to go out and experience the world and understand it better around them. But today, I'm going to talk to you a little bit about a story. This is a story of a solar storm called the Gannon storm. This is a true story. It happened a little over a year ago. In fact, many of you may have seen the effects of this solar storm. But I wanted to tell you the story from a science perspective to give you a little bit more insight about how we think of the sun and think of solar storms from a NASA perspective, and then give you some context that when you see phenomenon around you that are solar caused, that you understand a little bit of how it got to here and what's happening. Then I'll finish up with some projects about connecting communities to heliophysics with both IEI and the University of Alaska, and then we'll take some questions. So without further ado, let's plunge into the story of the Gannon storm. All right, so this image that you see was taken right at sunset, and you can see the sun, of course, in the middle of the image here, but you can also see some spots on the sun. Sunspots have been known for a long, long time, and all of the sun watching communities that have, actually stared at the sun, which is a challenging task. I would not recommend it without proper equipment, have seen spots. And so it is the longest running scientific record that we have in astronomy of people writing down the number of black spots they see on the sun. And you can see why, right at sunset, you can actually get a good glimpse of this. Or if there's a lot of smoke in the air, this is wildfire season out in the Western United States and Canada. So if there's a heavy amount of wildfire smoke, you can also get a glimpse of the sun in this way. And you can see dark spots, and these spots move around. And the particularly large spots right at the 6 o'clock position on the sun, that was the origin of this story. So this is the same region, that big black spot region, but looking in a little bit different views now. This is the birth or the origin of this active region. And that's what scientists call a collection of spots. On the left-hand side of the screen, you can see some of those dark spots sort of emerging from this colorized but white light view of the sun. But you can also see some light parts. It's called plage. It's French for beach, because I thought it looked sort of sandy. In fact, it's very much not sandy. It's quite hot, and this is the view of the active sun that scientists have been using for hundreds of years. On the right-hand side is a more contemporary view of that same region. This is a view of the magnetic fields of the sun. So this is the magnetic forces, that is the same magnets that you would put on your refrigerator or that drive your compass, but on the sun, they are incredibly strong and they're dynamic. They change. And on the right-hand side, you can see a colorized version of the magnetic fields where I believe the orange, yellow, red color scheme are magnetic fields coming out of the sun, and the blue and green magnetic field or colors are magnetic fields going into the sun. And so you can see this interesting complex pattern. It's not just a north-south like a bar magnet, but it's loops and it's little fragments, and that is what's underpinning that active region. So what is an active region? I sort of gave you a visual of it, but we can actually, using some modern simulation, we can actually go into the sun to understand it. And so this little short animation that I'll show you is a view inside the surface of the sun to help understand like where this idea of an active region came from, or is it orient. So you see these bright, shiny, silvery loops, which are representative magnetic fields. But these loops aren't just static. They actually emerge, they get pushed out, they're evected from the interior of the sun out through its surface. And those foot points, the origins of those loops, are what form sunspots, these dark spots in the sun. Then the loops, of course, can get complicated, and magnetic fields don't just stay static. They actually move around in the sun. And so this process of moving magnetic field from the interior of the sun to the exterior is the source of these magnetic fields or of these geophysical storms. When the magnetic fields get twisted and pinch, they can reconnect, like is showing here, and release a tremendous amount of energy as well as material into the space. So this sort of view of an active region is what scientists, contemporary scientists at Goddard, keep in their head when they're thinking about solar physics and storms, is this idea of magnetic fields moving and changing and causing eruptions or changes on the sun. But this isn't just a local phenomenon. This is a global phenomenon. So if we take image of the sun, these are actual white light images that are sped up over, I want to say, I think it's several years. I want to say it's about 12 years. You can see that there are changes happening in the sun. So these are sunspots that kind of appear and disappear. You have a little bar graph on the side showing you the number of sunspots appearing and disappearing. But if we cut an image into the sun or cut a wedge into the sun, as you can see here, there's some science that we can better understand these origins of sunspots. Again, it's magnetic fields. Those are represented by these brown, twisty lines that are coming out. And magnetic fields, even though, it's a field which is a very complex sort of relational idea in physics, I think of them more as rubber bands. It's helpful for me to think of them as rubber bands. So I'll invite you to do the same. Okay, so if we think of magnetic fields as rubber bands, you can take a rubber band and stretch it. You can twist it. You can put tension into it. And like a rubber band, though, if you keep on twisting it enough, it'll start getting kinked. I don't know if you had a little airplane like I did when I was growing up, where it's a balsa wood plane with a little rubber band connected to the propeller, and you could twist the propeller until the rubber band started kind of knotted. And if you kept on twisting it, it would actually end up making little kinks and twists in the rubber band itself. The same thing happens with magnetic fields. In the interior of the sun, the region called the solar dynamo, this place where the magnetic field is generated, ends up twisting the magnetic field so much so that they kink and push out to the surface, which forms sunspots and active regions. Then those active regions, they reconnect. It's like your rubber band on your airplane getting twisted too much and breaking and snapping. And then, I mean, I've had this happen to me many times where the rubber band snaps and it ends up snapping onto your fingers and it releases all of its energy in an instant, which is akin to magnetic reconnection, where these twisted magnetic fields are releasing their twistiness into a solar flare or into an eruption. This relieves the amount of twistiness in the field, which is a good thing. It relaxes the energy of the sun. And so then the number of sunspots fall down. This whole process of magnetic field getting more twisted and more complicated, and then releasing energy and relaxing back down to a quiet state again is called the solar cycle. And this solar cycle happens over about 11 to 12 years typically. So we go through phases of maximum, solar maximum, where there's a lot of sunspots and lots of magnetic fields coming out, and then solar minimum, where there aren't quite so many sunspots. So let's go back to our active region for the origin of our solar storm. Okay, so now that you have an idea of thinking about magnetic fields as these twisted rubber bands, and you have this idea that they actually are pushing out from the inside of the sun too. So keeping those both in mind, I'm going to play a movie now of this active region, these sunspots for the Gannon storm. We lovingly call this active region 3664. Uh, it's just numbers that NOAA assigns to the active region. But this active region starts to grow and change. So this is over about 11 days as this active region moves across the surface. So you can see immediately that things are changing quickly. This isn't changing on the course of 11 years or 12 years. This is changing on a course of 11 days. And things are getting much more complicated and actually much more dense too. So let's restart that again. Much more dense too. So the amount of magnetic fields, there are more magnetic fields getting pushed out, and then not only that, but being shoved around. You can see the sort of a flowing pattern in these sunspots, and it's getting more complicated and looking more angry. If we take a look within the magnet or within the sun, we can also get an idea of what else is happening. So it's not just magnetic fields because the sun, of course, is a hot ball of plasma. So this is an actual image of a sunspot. High resolution image. It's about a decade old, so we have a higher resolution image now. But this is a high resolution image of a small, simple sunspot. And a team did a deep analysis on what was going on beneath the surface, looking at waves and looking at essentially sunquakes. And when they were able to do that, they were able to actually map out the temperatures beneath the sunspot. And this graph is showing you the colors are showing you that temperature, so that the red is quite hot. It's a hotter than average, and blue is cooler than average. And what's fascinating about sunspots is that they actually, well, we'll let that play again, is they are actually doing two things. They're not only magnetic fields are coming out and getting pushed around, but it's actually suppressing energy coming out from the sun too. It's holding the hot plasma down into the surface of the sun, actually preventing that heat from escaping the sun. Well, that's one reason why the sunspot looks black is because it's cooler. So there's less energy coming out and less light coming out. It's quite hot still, 3,000 degrees, but not 6,000 degrees. So the it's suppressing energy, but that's just near the surface. Actually, what it's doing is it's plugging up the energy flow coming out to the surface, but it's creating this hot spot down a little bit lower in the sun too. So there's this tension building. You could think of it as like a volcano, for example, of where, a magma chamber is filling, and even though the volcano is relatively stable, there's this energy that's building up underneath that's being trapped by the plug in the top of the volcano. And a similar idea with magnetic fields, the magnetic fields are trapping the heat from being released and actually suppressing all that and keeping all of that energy bottled up into the sun. If there are ways for the sun to sort of flow and relax out, a lot of this energy just sort of dissipates and gets sort of blended in with the rest of the sun. However, in complicated sunspots, they can't do that. There has to be another way of energy release. There has to be this magnetic reconnection, this other way of releasing all of the energy that's being trapped. So let's go back to a magnetic field look at the sun. Okay, so this is that same active region, the 3664. And now we're going to look at this same active region, but using magnetic field measurements. So this is an image from the Solar Dynamics Observatory spacecraft, the HMI instrument. This is a magnetogram, which means that it's a picture of the derived magnetic intensities and fields on the surface of the sun. So you can see most of it is gray, which is our very low level magnetic fields. I mean, nothing, fairly weak fields. And then the white fields and black fields are the higher intensities. And I think the white field is, I always get this wrong. I think the white field is going into the sun and the black field's coming out of the sun. I could have that opposite. I don't quite remember. I always mess that one up. But the magnetic fields, these are magnetic fields that are perpendicular to the surface of the sun. So if we look at that same active region, that's the same video, just a different measurement as before, we can see that complex boiling pattern, those flows happening. But now it's not just one kind of sunspot moving around. There's actually two polarities moving. There's this tension and this dance between the positive and negative magnetic polarities of the sun. And as it rotates through, you can see how complicated, got some video artifacts there. You can see how complicated this is becoming. There's active tension and release between these two magnetic fields. These are two incredibly strong forces that are part of the same system, but actively working to pull against each other and working to move this energy around that's being trapped underneath. So this view, this magnetic view of the sun, is really where how scientists begin to think of solar active regions and the sun and how it behaves, because the sun is fundamentally made up of this ball of plasma, hot, superheated gas, and then magnetic fields, which move that gas around and drive it forward. So this is where I think anybody would look at that active region as it evolves and oh, come on. Huh, okay. Look at that active region as it evolves and think, boy, there is something happening here. It looks almost like a storm cloud erupting over the plains or some other incredibly dynamic phenomenon, like something interesting is going to happen here. And in fact, something interesting did. A lot of something's interesting. A whole bunch of them. So this is the number of solar flares. So these are bursts of X-rays coming from that single active region over a series of days. So on the plot you have on the y-axis you have the number of flares erupting, and on the x-axis you have the dates. Each column is 1 day long. The blue is what are called C-class flares. Those are sort of medium-sized flares. M-class flares are large flares, and X-class flares are incredibly large flares. And this is large in terms of the amount of energy that's released and the intensity of X-rays coming out of the sun. And so it starts off the active region, starts off fairly conventional, where there's a couple of large flares, but a whole lot of medium flares and even more small flares, which aren't even plotted here, all sort of releasing energy. But then on May 8th, 2024, there was an incredible change where the amount of energy and the number of flares spiked. And you can see on the 8th, 9th, 10th, 11th, 12th, culminating all the way on the 14th, there were massive X-class flares, one or two a day. I think there was three on the 14th, but then a tremendous number of M-class flares too. So this actor region became incredibly dynamic. It was erupting all the time. So what does an one of these flares look like? Well, to get a view on that, we have to go to space. Um, this is an image of the sun in 10 million degrees. It's also taken from the Solar Dynamics Observatory. So this is a false color image. It's taken in the extreme ultraviolet wavelength. This extreme ultraviolet, you're familiar with the ultraviolet that will, burn your skin or make you tan on a sunny day. If you go to shorter and shorter wavelengths from there, you get to the extreme ultraviolet, which is right next to the X-rays. So this is right almost the wavelength of X-rays. But this is a view of what the sun looks like at 10 million degrees. This layer of the sun is called the corona, the crown of the sun, the corona of the sun. And when the first thing you can notice is that it looks very different than the sunspots, the white light images, or the magnetic images that I was showing, the magnetograms that I was showing you. These are showing loops of material, superheated materials spiraling off the surface and being trapped on the sun. You can see all sorts of interesting patterns as the flows move around. This entire image here is dictated by the magnetic fields that underpin all of this. So all of these structures, the plasma is being pulled around by the magnetic fields. So all of the bright lines and loops and all of it is really caused by where magnetic fields are and where they're moving. So if we play an animation, this is an animation over about a day. You can see our active region about about the 4 o'clock position. And this is one of those eruptions. I think this is on May 10th, or May 10th or May 11th. One of those X-class flares. And you can see this is the animation still going, but you could see that pulsing brightness as the detector was saturated. So the pixels were so full of light that they couldn't handle it anymore, and then basically shorted out to a bunch of other pixels on it. And you got this incredible pattern. But you can also see if you have a keen eye that there is a bunch of static coming onto the camera as well. And that static are energetic particles coming from the sun, from an eruption as well. So this is what the solar flare looks like when you go out into space and look at it. Let me start that again. Yeah. So again, this is how the sun looks evolving over a course of hours. So we started off talking a little bit about the 11-year cycle of the sun, and then I was showing you an 11-day cycle of the sun. This is an 11-hour cycle of the sun. And what's amazing to me about the sun and what's so fascinating, or one of the things that's so fascinating, is that at every time scale that you can think of, the sun is changing and it's evolving and something is happening. And so even though we're not going to talk about shorter timescales than hours, if you look at minutes or seconds or milliseconds, it doesn't matter how short of a time scale you look at, there's something that's changing on the sun. It's incredibly dynamic. Or if you want to go the other way and think about how the sun changes over hundreds of years or thousands of years or millions of years, the sun does have those cycles as well. So these cycles inherent to the sun are how we understand the sun over long term and how we make predictions, because understanding these cycles is incredibly important to understanding life here. So that bright, flashing, pulsing, hot 10 million degree corona image wasn't actually even able to capture the full intensity and brightness of this. I think this flare ended up being something like 35 million degrees at its peak temperature, which is incredibly hot, and released as much energy as humanity has ever used, ever. If you take all of the energy that humanity's ever used, everything from campfires or fires all the way up to nuclear power plants to all of the energy ever used by humanity, that one flare has, I think it's something like 100 times bigger than that. So the incredible power of the sun is showcased in these images too. So this is just one of the flares, and there were many flares coming off day after day of that active region. We can also look off the sun. If we cover up the sun and play a movie of it, we can see the material coming off the sun. So this is a spacecraft called LASCO. LASCO is called a coronagraph, which means that it covers up the bright disk of the sun, represented by the white circle on this animation. And when you do that, then you can see material coming off the sun. And so at that exact, or right associated with that flare, was an incredible coronal mass ejection as well, where a bunch of mass got pushed off of the corona and into interplanetary space. What you can also see in this detector is the snow hitting the detector. That's actually from an earlier eruption of energetic particles that raced through space and ended up impacting this detector here. So all of that snow fuzz on the detector are energetic particles that came from an earlier eruption from that active region. But showcases again how big these features are. Because if you think of the sun is I think what you can fit about 100 Earths in the diameter of the sun. So you can fit. So I think to scale, Earth would be approximately the size of one of those little salt and pepper pixels. And you can see the size of that eruption coming off. It's tremendous. It is a huge amount of mass coming off. So at NASA, one of the jobs between NASA and NOAA is to be able to not only watch the storms as they emerge, be able to make some understanding of what's going on physically, but also to make a forecast. So that's what we're seeing here. I'm going to let this animation play a number of times. So on the top, you have the density of material coming through space, and on the bottom is the velocity of the material. So we have two views that we're representing here in this model of the solar system, where looking down from the top, that complete circle there is as if you were floating above the solar system, where the yellow dot in the middle is the sun, and then the green dot is the Earth. And this is all a mathematical model predicting what happened coming off of those eruptions. On the bottom, we have velocity. So this is how fast things are coming. So you have how much is coming, the density, and how fast it's coming. Then you have these graphs over on the side showing you when things are going to hit. So you have in the density, you have these three different lumps all hitting around the same or around a day apart from each other, as well as a speed at Earth, the solar wind speed of hitting, and it's a fast storm that hits in three different chunks. And the three different chunks, that's an important piece because solar storms do happen frequently. But what made this storm that we've been talking about, the Gannon storm, so powerful and impactful is the fact that it wasn't just an isolated event, that there were three storms that all were released in short amount of time, that all sort of stacked up next to each other, and in some cases merged together and created this superstorm, this solar superstorm. And the stacking of events are really what caused the storm of last May to be so huge. Um, the um, the other thing to notice, if you're a keen observer, you'll notice that a bulk of the storm missed Earth. It actually hit. It actually swept away from Earth. So we got a direct hit, but not the worst case scenario from even this storm. If we had been operating just if things were, I don't know, shifted by 15 or 20 degrees, it could have been significantly worse. So what does this look like when we come back down to Earth? Well, this is what the NOAA, the National Oceanic and Aeronautic Administration, National Oceanic Administration, does is make these both predictions and measurements near Earth. So the top plot, I'll describe it a little bit to you. This is the inner space environment right near Earth, and the bottom plot is how Earth is responding to that forcing. So the top is the interplanetary magnetic field, and the different colors you see on there. Don't worry if you can't read it all. You don't need to. But what I want you to notice here is that the different colors represent different components of the magnetic field, and they are wild. It's not just a wave coming through. It's not just like an ocean wave sweeping through and then it's quiet again. This is incredibly dynamic. Things are spinning around. It's a complex cloud of magnetism and plasma that's hitting Earth. It's this rolling wave of turbulence that ends up hitting Earth. Fortunately, Earth has a magnetic field, and we have an atmosphere. So most of this is being shed away from Earth and just shed away from Earth by Earth's magnetic field. And the atmosphere of Earth is absorbing any of the high energy particles. On the bottom, you can see the Earth's response to this. So this is the KP index, which is a measurement or it's an average of how the Earth's magnetic fields and Earth's currents are adjusting to that solar forcing. And the plots there, you can sort of intuit that green is pretty normal, yellow is a little bit stormy, red is quite stormy, and maroon dark red is very stormy. And you can see there's a couple of different times where this rolling magnetic field cloud that came sweeping out from the sun ended up causing a major storm here on Earth. But the way you may have seen it is something like this. This is aurora. So if you were able to see the Northern Lights on May 11th, 2024, this is approximately how far south the auroral oval it was, which means that if you were even down in New Mexico, Arizona, Texas, you were able to see the Northern Lights, which is pretty rare. If you happen to be in Michigan or Minnesota, you were looking directly up at the Northern Lights. This aurora borealis was directly above you. So this is a composite image from a NOAA satellite that is showing how this aurora appeared above the United States and Canada, and it was spectacular. So this photo was taken from Vancouver, British Columbia, by a NASA photographer, which is showing you this aurora coming down directly above her. She was looking directly up at the sky and seeing this aurora come down. And it's quite beautiful. The different colors represent the different species of material that's in the atmosphere, oxygen and nitrogen primarily. And it's amazing to see. I have to admit, sheepishly, I did not see the storm. I was up until 11:30 and I was just nothing happening and I went to bed. And apparently at about 12:30 is when it all hit. So I should have just stayed up a little bit longer. But plenty of people got really amazing photographs, including, I think, Chris has some spectacular ones from this storm. But this is sort of the beautiful side of things, but there's an impact side too, where it really comes down to the way we live here on Earth. The aurora and all of that energy that come into the upper Earth's atmosphere it deposit quite a bit of energy in the Earth's upper atmosphere, and especially near the poles, the closer to the poles you get. And so if you happen to be in an aircraft and are traveling near the poles, understanding that impact of that radiation dosage is incredibly important, as well as if you're an astronaut. But this is the little animation here as you see where air travel was diverted to avoid that radiation on May 11th compared to a week later on May 18th. And you can see that all the traffic coming from North America to Europe was diverted farther south, and that was precaution to make sure that people didn't, or especially pilots, passengers are. It's less of an issue because passengers are not flying as frequently, but pilots, it's a big concern because they're flying very often, and they want to make sure that they don't get a large dose of radiation. Second one is that it can cause disruptions in the ionosphere. These pockets of electrons form in the ionosphere, the one of the upper layers of the Earth's atmosphere, and this can make satellite signals that are passing through the ionosphere disrupt and then get distorted. So if you're relying on GPS, this is a big deal. Oftentimes in modern agriculture, people are using GPS to do precision agriculture, to lay down seed or fertilizer or water to use resources efficiently. And in one study out of, I don't think it was Iowa, I forget, it was somewhere in the Midwest, that this one storm cost an average of about $17,000 per farm because of GPS dropouts and distortions. $17,000 isn't a ton. It's not going to, bankrupt a farm. But if you add it up over all the farms that were affected, that's a significant amount of money. And so being able to understand the impacts of these storms has a real world monetary value of being able to advise people who are working the land. And finally, one of the most fascinating things that came out of this storm, in terms of scientifically, is that there were new radiation belts that were formed. Okay, so this is an image of the Earth. The white lines are the Earth's magnetic fields coming out. This is the white lines are what drives your compass to find the North or South Pole. The rainbowy colors are the intensity of electrons that orbit the Earth in a pretty normal way. These are called the Van Allen belts. They exist almost all the time, and that's yeah, pretty normal. You can get a second belt forming, which is actually the second belt in from the outside. So if you go from the outside, the next one in, that's a normal storm time condition where you get a second electron belt forming. The fascinating thing is that they got a new type of belt forming out of this. The first time it was seen, actually, was a proton radiation belt. So that's represented in purple here. So for the first time, we're able to observe not just that more material was put up in the radiation belts that surround the Earth, but it had a different composition. It was made out of protons. And if you happen to be launching a satellite or operating a satellite, this has big implications. And so you need to be able to understand how much and where protons and electrons will be in Earth's orbit because they're deeply impactful to satellites. All right, so I'm going to take a short transition here and talk to you a little bit about NASA's Heliophysics Education Activation Team. I mentioned a little earlier that this group is working towards educating both informal and informal learning how the Earth-Sun system works. Like the story that I told you of the Gannon storm, but all sorts of heliophysics aspects, all of that Sun, Earth, and solar system relationship, and how we live with a star next to us. This means that we need to be able to work with the communities that are not only deeply impacted by the sun, but also have unique perspectives. Which is one thing that led us to this coloring book project. So this is a project that we're doing with the Geophysical Institute at the University of Alaska Fairbanks to create a multi-page coloring book to talk through all of the different aspects of heliophysics. And what you're seeing here is a black and white graphic, sample graphic of the aurora that exists in the page of the coloring book. But we also recognize that people living at northern latitudes, extreme northern latitudes near the poles, have a very unique relationship with the sun because aurora for them aren't just a once in a while phenomenon when there's an exceptional storm, but a regular phenomenon. They see it often. In fact, the Geophysical Institute is one of the premier places in the world to study aurora. So people have been living, of course, up at that northern latitudes for thousands of years. And so one of the aspects of this coloring book and this project was to go out and talk with those people to understand the perspectives that people who have traditionally lived at those places understand and think about the sun. We working with the Geophysical Institute and their native partners across Alaska, we have 8 different Native Alaskan languages that we've captured relevant words, relevant ideas. And so, for example, this is this little piece that you see here is talking about the word for particles, which is literally dust or ashes. But it's how people have been talking about their relationship with the sun for much longer than NASA's existed, and much longer than any of the countries or modern systems have existed. Another project, and a similar sort of idea, is the project that we're doing with the Indigenous Education Institute. And this is really taking the ideas and the concepts of heliophysics, these deep ideas of the Earth-Sun relationships, and being able to translate it into a meaningful way into Navajo, and this translation process isn't just about capturing a word, but it's about capturing the idea and about the essence of what this relationship process is. And so you can see an example here of translated. I'm certainly not going to read it. Nancy, David, if you would like to, you're certainly welcome to unmute yourself and read the Navajo translation. But the English translation is the sun pushes out particles of itself, or it pushes out parts of itself as energetic particles like a wind, which envelops the Earth and all other planets. This is fundamentally describing the origin of the solar wind, but being able to phrase it in this way, it now has a translated component into Navajo, and we can actually talk in using that language system, use it to talk about heliophysics. You might be asking a little bit about like what would be the motivation of doing this? Well, I'm a strong believer, and there's good scientific evidence backing up as well, that the language that we use to talk about a thing or a phenomenon is it informs us deeply on how we think about it. So it's not just about being able to speak about something or communicate to somebody else, but it's a way we conceptualize and the way we hold it in our heads and a way we understand how systems fit together. Navajo being a very unique language compared to Western languages, understands the relationships between entities in a different way than Western society can, just by the language itself. The sun and the sun earth system is an incredibly complex and nuanced system where there are all of these cause and effects where they all sort of fit together in order to create this complex sun earth system. If there was a way that you could think in Navajo to understand the sun earth system, I think we could make some amazing advances in understanding this complexity just by using a different language. So that is sort of the ultimate goal behind this, but this is certainly the first step. For this, we are producing 3 different posters and an educator guide in order to better highlight these different aspects. So stay tuned for copies of that coming out. All of these resources, of course, we can find at our website, the science.nasa.gov/learn/HEAT, the heliophysics education resource database. These are all resources that are free. You can go and download them. You can use them in your classroom. You can use them in whatever learning environment that you want. But they're all aligned to science standards as well. And so using the framework for heliophysics education, we're able to take these and put them into a classroom context. So if you're a classroom teacher or if you need to be able to teach to national science standards, we have that ability to be able to matrix all of this through. The heliophysics resource database, which has an amazing number of resources, over 300 now, has images and lessons and graphics and videos, all in hopes that people will be able to teach and talk about the sun in a more concrete and coherent way. With that, thank you very much for your time. I certainly appreciate your attention, and I hope you have a lot of questions because this is just an absolutely fascinating topic for me, so I'm happy to answer them.
Thank you, Michael. What a great presentation. I missed a couple of the beginning slides of yours, so I'm going to sometime this afternoon go back and listen to the whole presentation with the slides. And I particularly loved what you said at the end, why this is important in terms of using the language you are using to speak about something. Um, it determines how you think about it and what discoveries could be made if you used a different language, especially one that's not a European, Euro-American language, because they're very similar. But I think that getting working with a group of people that have a completely different way of looking at the universe really can lead. We've always thought that, David Begay and I, that there would be some amazing discoveries that could be made if we followed this out. And thanks to our work with Michael, which has been really, really fascinating and rewarding, I think we're starting to see how that could actually happen. And so this, I think any of you that were listening to this start to get a glimpse of what kind of discoveries could happen by working together in terms of the languages and going deeper in terms of the concepts and thoughts that we share and how we can put things together in a way that's not so completely linear as has often happened in the past. So with that, I give you great thanks, Michael. And now I'm going to turn it over to Martin Storchdeck, who will field the questions and answers for this part of our webinar. I don't see a place up there at the bottom of my screen where you could have put in questions. I don't know if that means just me or all of you listeners, but you're certainly welcome at this point to put them in the chat if you want. So I will turn it over to Martin, who's
Oh,
another one of our respected and great colleagues.
thank you, Nancy, and thank you, Michael, for this presentation. And yes, the Q&A version functions. People have been putting questions in there. Um, and some of them have to do with understanding better. I will go to the more conceptual big questions in a moment, but let's just start with a question that is more, so to say, detailed about what you described, which is people were interested in the question of what what is the difference between a flare and a CME, and what do these things consist of? What is a flare? What are solar winds and flares? What is the material that actually hits us? What is the cannon fodder here?
Yeah, that's a fantastic question because there's a sort of a colloquial sort of interchange where people will use the word flare to mean any sort of eruption, or they will use CME to mean something else. So like those words have specific definitions when you're talking scientifically. So a solar flare is literally the light that is erupting from the sun. It's that flash of extreme ultraviolet and X-ray light that comes off from the sun when a magnetic reconnection happens, when one of those magnetic fields twists so much that it snaps and recombines and releases a tremendous amount of energy. It's that light energy that we see. That's the flare. The flare includes all sorts of energy, heat, and all of that, but it's the energy coming from the sun, and the light is what we observe. A coronal mass ejection, or CME, is the material that is pushed off from the sun. So that can happen with a flare. There are other mechanisms that can push material off the sun in great quantities as well. A filament eruption is one of them that happens frequently, where a big lofted piece of the sun becomes unstable and then is released out into the solar wind. So the coronal mass ejection is made up. It's an interesting, complex cloud. The material itself, like the physical material, is made up of electrons, protons, neutrons, and then little combinations, alpha particles. So like electrons and or yeah, electrons and neutrons, or excuse me, protons and neutrons stuck together into like fundamental elements. So those materials come is are in this cloud, but they're held into the cloud and are sort of turbulently held into a cloud by complex magnetic fields. And so it's this combination of particles but magnetic fields that come rushing through the interplanetary space and impact the Earth. The magnetic fields are shifted away by Earth's magnetic fields. Positive polarities repel each other, so those are shifted away. If they're opposite polarities, if they're the same polarities, they'll repel each other. If they're opposite polarities, they'll attract each other. But that's then sort of funneled into the Earth's magnetic field system. The particles, however, they will end up getting trapped in Earth's magnetic fields and rain down on Earth, specifically around the polar regions, which we see as aurora. So that's really the linkage there, is that it's the particles that are trapped by the magnetic fields that impact the aurora. So that's a long answer for the CME flare difference.
And can you say something about the solar wind in connection
Oh yeah,
to?
yeah. So the solar wind is the background component coming off the sun at all times. There are a few different sources for the solar wind, but it is always coming off the sun. So the sun is always pushing out material all the time. The solar wind has similar composition to CMEs, except the magnetic fields are very different. The magnetic fields are laminar. They're very smooth and sort of long, and they're not turbulent and kinked. And then the amount of material is significantly less, but it's the same makeup. It's just a matter of the complexity and the amount of it. So the smooth magnetic field lines and relatively low quantities of material make it for, it's not a friendly environment. You're not going to have a good time out there by yourself, but we can protect ourselves. We can protect our astronauts, our satellites, existing in that environment.
So when the sun shoots at us, so there's the laser from a flare, and then the alpha particles and stuff like that. How long does it take to reach us? There's a
Yeah.
there's a slight difference there, right?
Yeah, it depends. There are different speeds for these mass ejections, and some of it depends on has a coronal mass ejection swept through to begin with sort of clear out the way, create a wake, and then something can come in really quickly behind it. But the speeds vary quite a bit. I would say it takes at minimum 24 hours for a coronal mass ejection to get to us. It takes maybe up to 48 if it's a really slow moving system. So 24 to 48 hours is approximately it. 24 for a very quick one, and 48 for a very slow one. 36 is pretty typical. The solar flare, that light energy reaches us at the speed of light, so that's 8 minutes. So that's kind of where the prediction stuff can come in, is that we see the light, we see a flash, and then it's a race to figure out how is that whatever just happened on the sun, the solar flare, the coronal mass ejection, how's that changing? How did that erupt off? Is it going to hit Earth? And having to make those predictions in real time as we take measurements.
And now I'm shifting to the question of the relationship between NASA and Western science around heliophysics and indigenous ways of knowing indigenous science. There's a variety of questions
Mhm.
that asked about the connection here. Um, and one is, and I asked it from a broader perspective. You gave this example from heat and the language books and so on and so forth. Um, is there other connections that you're aware of when NASA takes into account, appreciates, uses, taps into, collaborates with indigenous knowledge systems here in the US or anywhere else?
Yeah, for heliophysics and for the sun specifically, there are a couple of points that have been really instructive and really helpful for our foundational understanding of the historical sun, using indigenous record keeping of specifically solar eclipses, and then to a certain extent sunspots. So solar eclipses are an incredible phenomenon where the moon completely blocks out the light of the sun. You can see the solar corona. Where those happen on the planet is incredibly important because it calibrates our understanding with how the Earth Sun system is changing over the long term, over hundreds or thousands of years. So using record keeping, whether it's etching or stories or any sort of oral tradition, to be able to pinpoint not only approximately when, but where, is really important, because the where part is the hard part. NASA can, you can build a mathematical clock where you just wind back eclipses, but it doesn't work like a gear turning. The system, the Earth, Sun, Moon system is changing, and it's evolving. And understanding that change and those evolving factors, like how fast the Earth is spinning, is changing just ever so slightly. So understanding where an eclipse existed is essential for that. And so understanding that perspective of not just when it happened, but where it happened has been, I mean, instrumental to understanding, the Earth Sun system over a long period of time. In terms of sunspots, the um, sunspots are our longest scientific record. Mostly in China, we've been relying on ancient manuscripts from traditional Chinese observing. So traditional Chinese observing, as in 1,000, 1,500 years old, to be able to actually reconstruct some of these points to follow a sunspot cycle back. Again, this text isn't just about, it's not about a scientific fact, although we put it in, but it's about where it happened, what were the observation quantities, how did they observe the sun system. So those sorts of having a longer view of time and history are really important for understanding the sun. Because as NASA, I mean, we've only been observing the sun for 60 years, and that's nothing compared to the length of the sun. So understanding some of these points, both location and technique, have really founded like the origins of how we understand the sun over long periods of time.
Thank you. Are you familiar with other projects, concrete projects? The question comes from Anne Zeiser, and she says, I know about Kate Citizen Science, other projects that you're familiar with, where NASA is directly not just working with IAI and the ones that he is working with indigenous communities anywhere else.
Yeah.
Projects.
So another project that comes to mind immediately is the Aurorasaurus project. So this is working with northern communities that regularly see aurora and being able to track when and where they happen. Again, auroral observations are really not that good right now, and so we rely on having a number of different locations and people taking photographs and recording when and where aurora happened to be able to reconstruct these individual phenomenon. So Aurorasaurus is a way that anybody can contribute to a database on when and where and what the structure of aurora is, and they've made genuine scientific discoveries using that. But it's because of the nature of aurora, it's all very much geared towards people who live at northern latitudes, so around the world.
Yes, a somewhat personal question. You
Yeah.
were part of the translation of this very interesting way in which heliophysics concepts were translated into or transformed into Diné and then back into English. Lauren here in the room, sitting next to me, asked through the Q&A, through this work in that process, the Navajo language, has any helio science concept become more clear to you in that like to what degree did that clarify for you yourself by engaging in this process?
Yeah, that's a fantastic question. So I think so far the clarity for me, like this is just the beginning of the project. So we're hoping to keep this going, and but the clarity for me really came in having to understand the all the different facets of the way these complex systems fit together. Because working with Nancy and David Nestor, we would put out, a phrase of something that is a very simple scientific idea in an English way of speaking, and they would come back and just say it just doesn't work. We just it just doesn't work for us. And so being able to think about like what the underlying meaning, like the deep physical meaning of what we're trying to convey by using this jargon or this specific text, and being able to repose the statements in such a way, it was really valuable because it made me think about those concepts deeper and try to understand, not just rely on the crutch of saying, electron proton, or for example, or solar cycle, or some of these things that are scientific jargon that are built up from a very fundamental scientific literacy standards in Western education, so that you learn what an electron is in elementary or middle school, and then you just build on that and build on that. But what does it actually mean? And that you just having that sort of self-reflection, I think, was the biggest thing for me. I do think that if we continue down this path, there will be other aha moments of how we actually understand and fit these pieces together.
Thank you. That's an interesting question about, so there's differences clearly indigenous ways of knowing and Western science, but here's a question in the question answer section that says, what difference do you see between different cultures within Western science? Let's say working with partners in Japan or elsewhere. Do you
Mhm.
see like different agendas, different ways of dealing with, like, is this a monolith, or do you see differences within Western science here that might be worth noting? Or
Oh, absolutely. I mean, not just differences within Western science, it's difference within subdisciplines of Western science. So, I mean, depending on if you're talking to somebody who specializes in Earth's atmosphere versus the sun versus the space weather aspect of just the heliophysics concept, you get different sort of subcultures of science that are coming out, and then on top of that, you have different ways of operating in a scientific way, compared to Germany versus France versus England versus the U.S. versus Japan. So there is an incredible diversity of just trying to communicate ideas across those different disciplines. One of the major challenges in science in general, but specifically heliophysics, is that you have these silos where you get these cultures of not just language, and you use specialized language to talk about your subdiscipline, but you get the culture of like what's important and how do you talk about what's important that are developed within these subdisciplines. And so even breaking out of that is challenging. So if I went to a plasma physics conference, for example, I study the sun. The sun is a giant ball of plasma. You'd think naively that going to a plasma physics conference should be fine. It isn't. It is an entirely different way of understanding what's important because of the way they pose the questions and the way they think about things. And so it's a challenge all over to do this sort of interdisciplinary, intercultural communications, even within science, like let alone talking to somebody who's an anthropologist. But like even within the physics field itself, yeah, it's the more you look at it, the more you realize, oh, we're just talking past each other. Yeah.
and I think soon I will have to hand it over to Nancy again. But before I do that, I'm going to test your ability to play poker. Because it comes from questions that are here as well. And that is, so just bear with me, stay cool. People ask, how does the current the budget process in Washington influence NASA's or your ability to work with indigenous communities? Is there
Mm.
an impact that you can see? What is of note here? Um,
So the budgets in Washington are incredibly challenging for science, all facets of science. It doesn't matter who or with whom you're working with. It is challenging environment. It will change in the next year. It will change. There will be a number of NASA missions that are slated right now for being turned off. We'll see if that comes through, but that is the current plan as it stands. There are going to be a number of research projects that are viable that will no longer continue, and given the current budget environment. So that's the reality of it. I think the working specifically with indigenous groups, the way we work with indigenous groups is going to change. The idea of education in this current environment is changing substantially. So the idea of education as a worthwhile thing to do the tone has shifted quite a bit. So it needs to be very much more goal driven or outcome driven. So that will definitely impact working with indigenous groups across the nation, across the world, because having clear objectives for understanding like why we're doing this and just saying to understand the world better isn't a good enough answer anymore. So that's I don't know how it's going to look, but that's the directions that we're heading.
And Nancy, is there room for one more question?
There's always room for one more
All right.
question.
All
They're
right.
great questions.
So here is now as Monty Python says to something, and he goes back to your own career path. But this is a question from Heather. What advice would you give to undergraduate students who are interested in heliophysics right now, in terms of what to do? I'm interested, now what?
Yeah, well, if you're an undergraduate interested in heliophysics, you certainly beat me out. I didn't know heliophysics was a thing until graduate school. So,
Yeah.
actually, I take that
Yeah,
back.
sophisticated undergrad, I guess.
I did meet a heliophysicist when I was an undergraduate and thought his job sounded incredibly boring. So, um, so I think what advice I would give is to focus in on something that is really just inherently fascinating, something that really just drives your curiosity. And that could be, I don't know, the idea of solar storms or of aurora or of launching a satellite into those Van Allen belts that I was talking about. Like it doesn't matter, but set your goal that you can wayfind against to something really spectacular, something that you just find inherently interesting, and then you'll navigate a path. Maybe it'll go through industry, maybe it'll go through NASA, maybe it will go through something else. But that I think having that fascination goal, that thing that just sort of drives your curiosity, whether you're paid for it or not, that is a way to keep you on that path to continue in the field.
But one thing you just mentioned, if you're interested in heliophysics, NASA is not the only place you can go later on. There.
No, not at all. NOAA is very interested in it. There's, of course, a space industry that is coming up strong. So there'll be industry jobs and private sector jobs. Of course, the military is very interested in it. So there's a lot of different aspects to it.
Yeah. So Godspeed to all of those who want to go into it. There's a big world out there. You don't just have to be a NASA scientist or a
Right.
professor.
Yeah.
I think at this point, these are the questions we had. There were some shout outs from people saying they want to use this material. There were some shout outs from people who said, how can we get high res stuff? It was answered already. So people want to see where the resources might be. People might use this stuff. So thank you very much. I think with that, I'll hand it to Nancy.
Okay. Oh gosh, thank you for this most interesting discussions and question and answers, Martin. Excellent job. And thank you, Michael, for wonderful answers. And I wish we could have continued on for another hour. I think one thing that is amazing to me is normally on these sessions, the people start dropping off somewhere in the middle or at the end. But in this case, almost everybody stayed on till the very bitter end. And the one that left apologized for leaving. And that was after our time slot was over. And so we were just delighted. I was just delighted to see it continue because I think the questions and the answers were so helpful to all of us. So I want to thank everyone that's participated. I will tell you, we've been recording almost all of the speakers' presentations. The only one we didn't get to record was John Harrington, the NASA astronaut, because the people he worked with wouldn't let him do it. They said, "Oh, if it's recorded, you'll never do another talk anywhere else because you've already said all you need to say." So that was kind of an odd thing, but we honored his request. Everybody else has been recorded. We had 20 in our first series. And Michael now is the first one of our new series, which is going to include a lot of non-native speakers as well as native speakers. We're trying to open the door and let all kinds of voices in here and different perceptions. And we think it's going to be extremely interesting. So you've now participated in the first one of the new series. And I want to especially thank Michael for bringing heliophysics down to earth, so to speak, and also for making it the human connection, because that is the name of our new series. And now we're beginning to see, thanks to this talk, that there's so many ways that the sun impacts us as humans. And this kind of research is extremely important. The recordings will contain the entire webinar, no cost to download them. And we are honored that many teachers and professors are downloading the recordings and using them in their classrooms as a valuable curriculum resource. That includes professors from Princeton and Harvard and many different schools too on the reservation, like Little Singer Community School and other schools off this reservation up in the Northwest. So we want to make it as accessible as possible. In closing, I want to extend a very special thank you to our technical support, Christopher Tarrant of Tarrant Solutions, Friday Harbor, Washington. Each time we host one of these speakers, there's so much work that goes on behind the scenes. And this time there was more than most times. The coyote factor, which is a Navajo disruptor and bringer of chaos, was hard at work trying to derail us right up to the point that this started today. So we're kind of chuckling about this, but Chris is the one who always comes up with a plan B or C to counter the possible chaos. Also, a shout out to Ashley Tarrant, who has created our beautiful poster. We will be sending out an email to you just after this presentation with a very short survey asking your reaction to what you have heard today. Please take the time to answer the questions because your responses are really helpful to us to inform our future program design. And with that, I will say from all of us to all of you, thank you, wado, ajeje, and gracias.